Dear students, in this video we are going to study about the electric current, conventional current, drift velocity, microscopic model of current, and also Ohm's law and its verification. Dear students, in this video we are going to study about chapter current electricity, and by studying this chapter you are able to understand about the flow of charges in a metallic conductor, Ohm's law, electrical resistance, and VA characteristics. Next, we are going to study about carbon resistors and combination of resistors. Next, Kirchhoff's laws, resistance bridge and its applications, electric power and electric energy, heating effect, Joule's law and its applications. Then, finally, we are going to study about thermoelectric effects by Seebeck effect, Peltier effect, and Thomson effect. Let us have a small introduction about this chapter. So we have already studied about the properties of charges when they are at rest, but in reality the charges are always in motion within the materials. For example, the electrons in a copper wire are never at rest and are continuously in random motion. Therefore, it is important to analyze the behavior of charges when they are in motion. The motion of charges constitute an electric current. And what is current electricity? That is the study of electric charges. And it owes its origin to Alessandro Volta, who invented the electric battery which produced the first steady flow of electric current. Modern world depends heavily on the use of electricity, and it is used to operate machines, communication systems, electronic devices, home appliances, etc. In this unit, we are going to study about the electric current, resistance, and related phenomenon in materials. Now let us see what is electric current. You already know that matter is made up of atoms. Each atom consists of a positively charged nucleus with negatively charged electrons moving around the nucleus. Atoms in metals have one or more electrons which are loosely bound to the nucleus, and these electrons are called free electrons, and it can be easily detached from the atom. The substances which have an abundance of these free electrons are called conductors. These free electrons move randomly throughout the conductor at a given temperature. In general, due to this random motion, there is no net transfer of charges from one end of the conductor to other end, and hence no current in a conductor. When a potential difference is applied by the battery across the ends of the conductor, the free electrons drift towards the positive terminal of the battery, producing a net electric current, and that is easily understandable from the analogy given in this figure. You see, so equal gravitational potential, there is no water flow here. Whereas here water will flow from higher gravitational potential to the lower gravitational potential. In the same way, electric current will also be from the higher potential to lower potential as shown in this diagram. Next, we are going to study about the mass moving from higher gravitational potential to lower gravitational potential. So, in this case, the positive charge will flow from region of higher electric potential to the region of lower electric potential. Negative charge will be flowing from the region of lower electric potential to a region of higher electric potential. For that, the battery or electric cell will simply create the potential difference across the conductor. Now, in this case, the electric current in a conductor is defined as the rate of flow of charges through a given cross-sectional area, and it is shown in this figure 2.2. If a net charge Q passes through any cross-section of the conductor in time t, then the current is defined as I is equal to Q by T. But charge flow is not always constant, hence current can more generally be defined as I average equal to delta Q by delta T. And this delta Q is the amount of charge that passes through the conductor at any cross-section during the time interval delta T. If the rate at which charge flows changes with time, the current also changes. The instantaneous current I is defined as the limit of the average current as delta t tending to 0. So I is equal to limit delta t tending to 0, delta q by delta t is given by dq by dt. And the SI unit of current is given by ampere and denoted by letter capital A like this. And 1 ampere is given by 1 coulomb per second. And that is 1 ampere of current is equivalent to 1 coulomb of charge passing through a perpendicular cross section in a conductor in 1 second. And you know that the electric current is scalar quantity. Next we are going to study about the conventional current. Here the direction of current is shown like this, that is from the positive terminal of battery through the bulb it goes to the negative terminal. But actually the electron flow will be in the opposite direction to that of the conventional current. So here in an electric circuit the arrowheads are used to indicate the direction of flow of current like this. By convention this flow in the circuit should be from the positive terminal to the battery and positive terminal of battery to the negative terminal of the battery. So this current is called the conventional current or simply the current in the direction in which a positive test charge would move. In typical circuits, the charges that flow are actually electrons from the negative terminal of the battery to the positive terminal. As a result, the flow of electrons of the direction of conventional current point in opposite direction as shown in this figure. Mathematically, a transfer of positive charge is the same as a transfer of negative charge in the opposite direction. Here, the electric current is not only produced by batteries. In nature, lightning bolt produces enormous electric current in a short time. During lightning, very high potential difference is created between the clouds and ground, and hence charges flow between the clouds and ground, like this.
In a conductor, the charge carriers are free electrons. These electrons move freely through the conductor and collide repeatedly with the positive ions. If there is no electric field, the electrons move in random directions, and hence their velocities are also randomly oriented. On an average, the number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. As a result, there is no net flow of electrons in any direction and hence there will not be any current. Suppose a potential difference is set across the conductor by connecting a battery, an electric field. E is created in the conductor. This electric field exerts a force on the electrons, producing a current. The electric field accelerates the electrons, while ions scatter the electrons and change the direction of motion. Thus, we see zigzag motion of electrons. In addition to the zigzag motion due to the collisions, the electrons move slowly along the conductor in a direction opposite to that of E as shown in the figure 2.4. This velocity is called drift velocity Vd. The drift velocity is the average velocity acquired by the electrons inside the conductor when it is subjected.
Now let us see how to define the drift velocity. The drift velocity is the average velocity acquired by the electrons inside the conductor when it is subjected to an electric field. The average time between two successive collisions is called the mean free time, denoted by letter tau. The acceleration A experienced by the electron in an electric field E is given by this expression. A is equal to minus E by m, as F is equal to minus E times E. The drift velocity Vd is given by the expression Vd equal to A tau, or Vd can be written as minus E tau by m into E. So the drift velocity is given by minus mu E, where this letter mu is given by E tau by m, and that is called the mobility of the electron, and it is defined as the magnitude of the drift velocity per unit electric field. So the expression for mu is given by Vd by E, and the SI unit of mobility is given by m square v power minus 1 s power minus 1. Now the typical drift velocity of the electrons in the wire is about 10 power minus 4 meter per second. If an electron drifts with this speed, then the electrons leaving the battery will take hours to reach the light bulb. Then how it is possible that the bulb glows immediately after we switch on the battery? Here, when the battery is switched on, the electrons begin to move away from the negative terminal of the battery, and this electron exerts a force on the nearby electrons. This process creates a propagating influence, which is called as the electric field, that travels through the wire at the speed of light. In other words, the energy is transported from the battery to bulb at the speed of light through propagating influence, that is the electric field. Due to this reason, the bulb glows as soon as the battery is switched on. Then we are going to study about some misconceptions regarding this topic. There is a common misconception that the battery is the source of electrons, but it is not true. When a battery is connected across a given wire, the electrons in the closed circuit start flowing through the conductor, resulting in the flow of current. Battery sets the potential difference, that's the electrical energy due to which gives the electrons in the conducting wire flow in a particular direction. The resulting electrical energy is used by the electric bulb, electric fan, etc. Similarly, the electricity board is supplying the electrical energy to our homes. The next one is about the usage of phrase like charging the battery in my mobile and my mobile phone battery has no charge, etc. But these sentences are not correct. So when you say that the battery has no charge, it means that the battery has lost its ability to provide energy or provide potential difference to the electrons in the circuit. When you say mobile is charging, it implies that the battery is receiving energy from the AC power supply and not the electrons. Next, we are going to study about the topic microscopic model of current. For this, let us consider a conductor with area of cross-section A and let an electric field E be applied to it from the right to left. Suppose there are n electrons per unit volume in the conductor and assume that all the electrons move with the same drift velocity Vd as shown in this figure. The electrons moving with the drift velocity Vd through a conductor of area of cross-section A. The drift velocity of the electrons is given by Vd. If the electrons move through a distance dx within a small interval of time dt, then Vd is given by dx by dt and dx equal to Vd times dt. Since A is the area of cross-section of the conductor, the electrons available in the volume of length dx is given by volume into number of electrons per unit volume, that's given by A dx into n. So substituting for the value of dx in the equation 2.7 in 2.8, we have A times Vd dt in n. The total charge in the volume element dq is given by charge into number of electrons in the volume element. So dq equal to E times AVD dt into n, and hence the current is given by I equal to dq by dt. We have I equal to NEAVD. Now let us see what is current density, J. The current density J is defined as the current per unit area of cross-section of the conductor. That's given by J equal to I by A. The SI unit of current density is A by m square or ampere per meter square. That is am power minus 2. And J is given by NEAVD by A from the equation 2.9. Therefore, the expression for the current density is given by J equal to NEVD. This expression is valid only when the direction of current is perpendicular to the area of cross-section A. In general, the current density is a vector quantity and it is given by J equal to NEVD. Substituting the value of Vd from the equation 2.4, we have the expression J is given by minus Ne squared tau by m times E vector, that's given by J equal to minus sigma E. But conventionally, we take the direction of current density as the direction of electric field. So the above equation can be written as J equal to sigma E, where sigma equal to Ne squared tau by m, and that is called as conductivity. The current density is a vector quantity and it is given by this expression J equal to Ne times Vd. And substituting Vd from this equation 2.4, we have J equal to sigma minus sigma times E. But conventionally, we take the direction of current density as the direction of electric field. So the above equation can be written as J equal to sigma E. But the sigma is given by Ne squared tau by m, and that is called as conductivity. The equation 2.12 is called the microscopic form of Ohm's law. The inverse of conductivity is called as resistivity rho, and the expression for rho can be written as 1 by sigma equal to m by n squared tau.
Hi, I'm George Simon OHM, and Y law states that the potential difference across a given conductor is directly proportional to the current passing through it when the temperature remains constant.
Next we are going to study about Ohm's law. The Ohm's law can be derived from the equation J equal to sigma E. Consider a segment of wire of length L and cross-sectional area A as shown in figure 2.7. When a potential difference V is applied across the wire, a net electric field is created in the wire which constitutes the current in the wire. For simplicity, we assume that the electric field is uniform in the entire length of the wire. Then the potential difference V can be written as V equal to E times L. As we know, the magnitude of current density is given by J equal to sigma E. That's given by sigma times V by L, substituting for the value of E. But J equal to I by A, so we can write the equation 2.14 as I by A equal to sigma into V by L. By rearranging the above equation, we can get V equal to I times L by sigma A. That is quantity L by sigma A is called the resistance of the conductor, and it is denoted by the letter R. Here we should note that the resistance is directly proportional to the length of the conductor and inversely proportional to the area of cross section. So the macroscopic form of Ohm's law can be stated as the potential difference across a given conductor is directly proportional to the current passing through it when the temperature remains constant. The expression can be written as V equal to IR, which in another form can be written like this. You can draw a triangle like this and divide it into two. In the upper part we can write V, and in the lower part we can divide it into two. On this left hand side we can write I, and on the right hand side R. So if we want to find out V, we can write it as V equal to I into R, the lower part of the triangle. And if we want to find out I, that's given by the ratio of voltage to the resistance. And if you want to find out R, that's given by the ratio of voltage to the current I. Then from the above equation, the resistance is the ratio of potential difference across a given conductor to the current passing through the conductor. Therefore, R can be written as V by I. What is the SI unit of resistance? That's given by ohm, represented by the symbol omega. So from the above equation 2.16, we infer that the graph between current versus voltage is a straight line with a slope equal to the inverse of resistance R of the conductor, and it is shown in this figure 2.8a. This is the slope, and this is the graph drawn between the values of voltage and the current. And here this is the current against voltage for a conductor which obeys Ohm's law, and this is the graph for non-ohmic devices, that is, they will not obey Ohm's law. What are ohmic materials? These are the materials for which the current versus voltage graph is a straight line through the origin, and they will be obeying Ohm's law, and their behavior is said to be ohmic. That is shown in this diagram A. Similarly, the materials which are the devices that do not follow Ohm's law, they are said to be non-ohmic, and these materials have more complex relationships between voltage and current. The plot of I, current, versus voltage V for a non-ohmic material is non-linear, and they do not have a constant resistance. That's given in this diagram B. Here, to verify Ohm's law, we have got a resistance and a battery of about 1.5 volts, and for which the resistance value is about only 10 ohms. Therefore, a large current will flow through this conductor, and if we increase the voltage to about 3 volts, then the current value will also be increased. But if we increase the resistance value like this, the current will start decreasing. And for maximum resistance, the current value will be minimum for this voltage of 3 volts. And if we increase the voltage to another 1.5 volts, adding that, we have 4.5 volts, and the resistance value is about 1000 ohms. Maximum value for which the current will be 4.5 milliampere. And if we are decreasing the resistance value, you can see that the value of current increases. And if we are increasing the voltage further, so there are about 4 batteries connected in series, there will be about 6 volts, and the current value will start increasing to decrease the resistance. And if we increase the resistance value to maximum of 1000 ohms, the current value will be minimum, about 6 milliampere only. Like that, you can also increase the voltage to about 9 volts, and for maximum resistance, the current value will be minimum 9 milliampere only in this circuit.